Hello everyone, my name is Eren Aydemir. I am going to present our work LiDAR-Camera fusion for depth-enhanced unsupervised odometry. System architecture of an autonomous vehicle consists of three modules: sensing, computing, and actuation. Autonomous vehicles to recognize the environment use various sensors such as camera, LiDAR, and GNSS. An essential component is computing. It uses sensor data to perceive the environment so the vehicle can compute its trajectory and calculate high-level actuation commands in control. Safety in autonomous vehicles is a high priority issue. Therefore, the perception modules must calculate the accurate position of both the ego vehicle and other objects in the surrounding scene. Once the obstacles are detected, the trajectories of other moving objects can be estimated. Mission planning and decision-making modules use these estimated results to determine an appropriate position to which the ego vehicle should move. Planning module generates trajectories following the output from the decision-making. Once local trajectories are determined, autonomous vehicles need to follow them. Motion control generates the actuation commands for the ego vehicle. As we can see, localization is one of the highest priority issues, and even though recent advances in computer vision, we can say that driving a vehicle on highway on a sunny day can be considered as a solved problem. In general, we are far from having ultimate localization algorithm that can handle all driving scenarios. If we think of a vehicle without a steering wheel, being able to drive anywhere, anytime, under any condition, this problem is much more difficult. Of course, localization of an ego is a long-standing problem in the literature. Many studies exist in the classes of visual odometry or SLAM. First known visual odometry real-time implementation on a robot is by Hans Moravec for Mars rovers using one sliding camera. From 80s to 2000, the visual odometry research was dominated by NASA JPL in the preparation for 2004 Mars mission. In 2003, a paper that initiated SLAM research by Davison. In 2004, visual odometry used on a robot on another planet Mars rovers Spirit and Opportunity. Visual odometry was reviewed in an academic environment by David Nister visual odometry paper. The term visual odometry became popular. In 2007, 14, and 15, many practically successful real-time capable algorithms developed in the geometry-based approach. In the growing era of deep learning, learning-based algorithms are also investigated starting around 2015. In the meanwhile, multi-modal solutions made prior algorithms more robust. In 2020, hybrid algorithms that combine both worlds, learning and geometric, become new state of the art. Lastly, fusion of point cloud and visual data in odometry frameworks has also emerged, and multi-modal solutions improve the performance even more. In this study, we are also relying on hybrid odometry framework. We propose first hybrid visual LiDAR odometry method that benefits from both learning and geometry-based techniques in an efficient framework. We developed the camera LiDAR fusion method. This fusion of sparse LiDAR depth map and dense image-based depth map is utilized for a more robust and accurate odometry results. This simple but effective visual LiDAR depth map fusion algorithm combines depth priors in a Bayesian framework by using confidence of estimates. Our hybrid visual odometry framework consists of several components. FlowNet is unsupervised optical flow estimation network, and it estimates forward and backward flows. DepthNet is stereo-trained unsupervised molecular depth estimation network. Key information for estimating the pose is extraction and matching of features. Not all pixels are predicted with high accuracy by FlowNet. Sparse matches are required to find enough number of correspondences. Inaccurate flow estimations are eliminated by checking consistency of forward and backward flows. Correspondences are selected from the pixel which have high consistency. Our aim is to combine multi-modal information in a hybrid odometry framework. LiDAR measurements are used to correct depth-net estimations for the pixels where accuracy needs improvement. Better depth estimations results better scale correction of pose estimations. Fusing sparse LiDAR measurement with dense visual information is not an easy task. 3D 2D correspondence calculation is difficult due to sparse nature of LiDAR. This type of methods are prone to error because of inaccurate matches. In our method, we first transform LiDAR measurements to the camera frame and project them to an image frame using known intrinsic and extrinsic. Then we prefer to fuse information for pixels where both measurements exist. Our proposed fusion algorithm calculates confidences of the inputs coming from depth-net on LiDAR depth map. Reprojection error is calculated between an image frame and its synthetically constructed version from depth values for both of them. Confidence is inverse proportional to the reprojection error. Lastly, confidences are used to weigh depth maps in order to have fused, better and accurate depth estimation. Pose estimation is made by two methods, 2D to 2D and 3D to 2D. Pose is estimated based on 2D to 2D correspondences. They are utilized in epipolar geometry to find the pose by estimating essential matrix. Translation recovered from essential matrix is up to scale. Due to that, triangulation is performed for 2D to 2D correspondences to recover up to scale depth value. When relative motion is small, solving essential matrix becomes unstable in practice. In order to avoid where this problem occurs, 3D to 2D correspondences are also used. 3D to 2D correspondences are 3D points in a view and its corresponding projection in another view. Pose estimation using 3D to 2D correspondences can be made by PMP algorithm. Solving PMP problem requires accurate estimation of the depth. Our fusion method helps in this point as well. Scale factor S in 2D to 2D pose estimation is predicted by aligning triangulated depth with fused depth map estimation. Predictions of the depth net are scale consistent and it's improved by fusion. Our camera LiDAR fusion method in hybrid visual odometry framework is tested using Kitty odometry dataset. Sequence 9 and 10 are used to report relative rotation and translation errors and absolute trajectory error. Our work has been compared with many state-of-the-art methods that use geometric, learning and hybrid approaches. Our LiDAR-Camera fusion solves scale ambiguity problem of a monocular camera and reduces translational drift significantly. The smallest error in the presented literature results is reduced by 44%. On this video, we can see the following. Feature correspondences obtained from the forward and backward optical flow estimates using consistency measure. Depth estimate from a depth net and LiDAR depth map. As it can be seen, LiDAR measurements are sparse and in order to fuse them, we can only use LiDAR points that are in the camera's field of view. By computing the confidence values of the depth maps, we fuse measurements and obtain fused depth map. These two sensors are complementary. That's why the resulting depth is more accurate. Using the fused depth and feature correspondences, we recover the pose. the computed trajectory is presented by green color, while the ground truth is red. As shown from these results, our proposed method produces good pose estimation. Compared to the works in the literature, we either outperform or produce comparable pose estimation accuracy. We have seen that localization algorithms can be classified as geometry-based, deep learning, and hybrid algorithms. Geometry-based algorithms are accurate but calibrated for particular applications. On the other hand, deep learning algorithms are dependent on the dataset and perform poorly in unseen environments. Hybrid approaches using monocular cameras do not accurately represent 3D structure of the environment and result in a drift. Our work is first hybrid visual LiDAR odometry method that benefits from both learning-based and geometry-based techniques combined in an efficient framework. It uses fusion of two complementary sensor measurements to achieve more robust and accurate localization. The proposed fusion method combines sparse LiDAR depth map and a dense image-based depth map to improve scale recovery and reduce average translational error. Since scale doesn't affect rotation estimation, we have noticed rotational drift in our pose estimation results. In the future work, we plan to reduce rotational drift by generating more accurate correspondence matches from LiDAR and camera.